I'm going to talk about mainly human impacts in the Holocene period on the Hungarian landscape, and particularly on the Great Hungarian Plain, because the project in scope of which I'm invited is dealing with coppicing. I will also touch upon this subject briefly. And I think the Hungarian landscape, particularly the lowland landscape, via the Pannonian influence, even in the Czech Republic, is directly connected to the vegetation history of this area. So maybe some aspects will also be beneficial for scientists who work in this area. I'm sure most of you have seen this picture before about the Pannonian Basin, but the reason I selected it as a starting point is to highlight that despite we hear most often the Hungarian landscape as a very dry land, particularly the Hortobágy area is a puszta area with salt steppe. If you look at the inundation and flood situation in the basin, this map shows the seasonally or annually water-covered areas in the basin before the channelization of the major rivers. Particularly the Tisza River, which is flowing in the east of the country, in the past, before the canalizations, inundated extremely large areas, mainly during the springtime and early summer. And also the same is true for this northwestern part of the country, which is directly connected to the northwest Pannonian grasslands, has received ample water in the past. But it's also important to point out that this water was seasonal, so appeared only part of the year, and this did not mean that by the end of the summer the whole area was not dried out. It could appear, but what you see in the landscape today is largely artificial. So without the canalization, our lowlands would be much wetter, and the groundwater table would be much higher. There was a large effort during the socialist time to reconstruct the potential natural vegetation of the country, and you see the end product of this. This map has been compiled by the Botanical Research Institute in Vácratúd, and the chief scientist was Bálint Zolyomi, who spent most of his time traveling around the country, looking at the remnants of the natural vegetation, and he was also specialized in pollen analysis, so he knew a lot about the history of the landscape, and he pulled up all this information to create a vegetation map that delivers information on the potential vegetation of the country. I know the same map from the Czech Republic, where botanists used a similar approach, but in comparison with the Czech map, I have to say that the Hungarians could rely on less paleoecological information than the Czech botanists who compiled similar maps. So this map largely reflects ideas of the landscape, and very little direct paleoecological and pollen analytical results is embedded in it. If you look at this map, particularly the Great Hungarian Plain, you see in blue the gallery forest and the floodplain forest. They occupy on this map quite large areas, mainly reflecting the inundated habitats. Also important, colored by pink here, the different saline steppe areas, mainly in the Hortobágy, but also in the Sárrét area south of the Hortobágy. So according to this map, the potential natural vegetation of the Great Hungarian Plain was in the past partly naturally open, partly covered by saline, wetland saline grasslands, and very importantly, in yellow you see the loess steppic grasslands. These also included loess forest steppe areas. So according to the description of this map, the potential vegetation in these areas marked by yellow is wooded steppe or forest steppe, dominated by oak, with considerable share of steppic grasslands. So that's the potential vegetation without human impact under the modern climate. The first thing that comes to my mind when I look at this picture, that our Hungarian plain in the Holocene, in the end of the Holocene, without human impact, would have been covered by forest steppe with a considerable share of open land naturally. This was explained by both climatic and edaphic conditions, particularly if you look at the Danube-Tisza interfluve area. Here you see a mosaic of sand oak forest and sand steppe grasslands. This is the less productive landscape of Hungary, and this is where we find in the potential vegetation also, but in today's vegetation as well, the largest share of sand steppes that are considered to be natural in this area. And this is the driest part of the country with the hottest summers and the lowest annual precipitation. So just to summarize, the map shows a really mosaic vegetation pattern, a lowland vegetation that's strongly influenced by hydrology and base rock, and particularly important are the loess and sand steppe grasslands with oak woods that are assumed to be natural. So with this mapping, knowing this map, of course the question arises whether we can prove that the natural vegetation of the Hungarian plain would be half wooded, half open without human impact. And of course one way to test it is to use paleoecological methods. Pollen analysis and plant macrofossil analysis are suitable to investigate these questions. This map, this slide shows you the possible targets of paleoecological analysis in the Great Hungarian Plain. There is ample seasonal water, as you have seen, but unfortunately the water table fluctuation, the groundwater table fluctuation is very high in the lowland, and therefore any sediment that accumulates mainly in these paleochannels, classical oxbow-shaped paleochannels, are affected by seasonal groundwater movements. So not the most ideal subjects of paleoecological research, but some of them still preserve continuous sediments since the formation of the oxbows. And of course the formation of these oxbow lakes extends back to the last glacial period. It very much depends on the channel migration, but both the Tisza and the tributaries of the Tisza River and the Danube River has flown through the Great Hungarian Plain, of course many glacial periods before, but the last remnants of these abandoned and sometimes buried paleochannels can be dated back to 30-50,000 years. The even older ones are buried under the younger Holocene and glacial alluvium, so they are very difficult to find. But relatively easy to find on the landscape, these paleochannels that date back to 30,000 years. And of course the most abundant are the Holocene paleochannels that were abandoned during mainly during the early Holocene, but there are some mid-Holocene and late Holocene meanders as well. So we usually select one of these infield paleochannels for paleoecological study in the Great Hungarian Plain. And depending on where we are in the Hungarian Plain, the sediment can look quite differently, but generally if it's a calcareous setting, we usually find a sediment series very similar to this. This is coming from the eastern part of the country. The site is called Kokad, very near to the city of Debrecen, near to the Romanian border. We have worked on this sediment recently and dated it. It's a 5-meter long sediment, and as you see, the bottom part is characterized by fluctuation between silty and burnt peaty material. This is a typical infusion loess, we call it, what was formed in a deflation hollow, which was seasonally wet or permanently wet during the glacial times. and it is quite typical for the period between 25 and 14,000 years, what we call the upper planiglacial period. We see burnt horizons in this sediment. The organic content is usually very low, up to 5%, and very rich bryophyte remains and often plant macrofossils that were accumulated in an environment very similar to the modern Siberian permafrost sites. So we believe, there are data that these were under permafrost and permanently wet during the upper planiglacial period. But also very characteristic for these deposits is with the late glacier warming, a change in the sediment composition. It becomes more clay, more carbonately rich. When the permafrost melts in the area, then chemical weathering starts and a lot of calcium enters the basin from the accumulated loess. And that's the time period when we have chalk formation in these lowland basins. And typical carbonate-rich shallow lake environments that accumulate very organic poor deposits. Pollen preservation sometimes good, sometimes bad in these deposits. Formerly, researchers thought that the chalk accumulation, so these very carbonate-rich shallow lake phase, was in the early Holocene, but radiocarbon dating of these deposits in the last couple of years proved that this chalk accumulation already started in the Younger Dryas and the Allerud period, so they are older. And as we enter to the Holocene, this is the Younger Dryas Holocene transition here. These lakes usually transferred into a very productive eutrophic shallow lake environment, and later on they became covered by usually phragmites, so reed beds, and become peaty. That's a typical succession of a paleochannel that's going back to 25-30,000 years old. Of course, the Holocene paleochannels doesn't have such a complex stratigraphy. They are usually characterized by either chalk deposition at the bottom, or if it's not calcareous environment, then we have silty deposits that are usually continuous until the mid-Holocene, and then similar peat deposits accumulate in these basins. Because of the fluctuating water table, however, it's difficult to build age depth models for these deposits, because the sedimentation is either not continuous or continuous, but the sediment accumulation rate is very, very much variable. So you have to bear in mind that in any of the lowland deposits, it's always a challenge to find the best sites that are continuous and to provide a good enough age depth models for these deposits. And before going into details of the lowland human history and the lowland vegetation succession in the Holocene, I wanted to point out for you, and I go back 2-3 slides here to the potential vegetation map, the difference between the eastern part of the country and the western part of the country. Even on this map you see that the western part of the country is much more forested. Usually Turkey oak forest predominate in the lowland environment, but as we move towards the west, and the influence of the Alps creates wetter conditions, and the altitudes are also higher here. Pinus sylvestris appears in oak forest here, and we also have some spruce forest naturally in the landscape. Even in the early 50s, 60s, with the advent of pollen analysis, or a big improvement in pollen analysis, we saw already that there are differences in the Holocene vegetation succession of the eastern side of the country and the western side of the country. And in these two slides, I just selected 2 pollen diagrams to demonstrate the major differences that are probably not that you are probably not that familiar with, because these were never published very directly in any foreign language. I will talk about this core called Sallóhát. This is a typical oxbow lake near the Tisza River in the central part of the Great Hungarian Plain. And we are lucky to have a very good time control on this pollen diagram and a very detailed pollen analysis here. But usually our Holocene forest succession in this part of the country starts with the expansion of elm, ulmus, around 11,700 years ago approximately. And you see an early Holocene phase up to 10,200 years ago, where you see a mixture of Betula, Pinus, Ulmus, Fraxinus, Corylus and Quercus are present in the landscape, but not that frequent. And the expansion in the lowland areas of Corylus and Quercus usually starts at 10.2 K, which is a short-term climatic fluctuation period, but we won't talk about it today. And as you see, Quercus is the first. So we have oak forest expansion first, which is very quickly followed by the expansion of Corylus. And then the mid-Holocene is characterized by the mixture of these, the dominance of these two species. Corylus is much overrepresented, as you will see, so its share in the vegetation is less than it's suggested by the pollen diagrams. But until 5,400 years, this is the typical picture. And then Carpinus betulus arrives also in the Great Hungarian Plain. Today it doesn't play a role in the lowland forest, only in the northeast corner of the Hungarian Plain. There is a phase with high Corylus pollen percentages, and then Fagus beech also appears in the central and northern part of the Great Hungarian Plain. So this is typical for the eastern part of the country. And as we move to the west, this diagram represents the area of Lake Balaton. It comes from the northern shore of Lake Balaton. A peat bog has been studied by Zsófia Medzikratski. Again, the time control and the age depth model is based on more than 12 radiocarbon dates here, so it's quite reliably captures the timing of the vegetation changes, and you see a totally different picture. The most important difference is Pinus here, which is usually in the western part of the country, dominates the pollen assemblages up to 8,600 Kbp. So it's not just the Lake Balaton sites, not just the northern area of Lake Balaton, but any pollen diagrams, if you look at from the western part of the country, you will see the persistence of Pinus in the landscape. And I go back again to this potential vegetation map just to show you why is this Pinus survival into the Holocene and how it can be explained. These areas south of Lake Balaton are very sandy. Sand dunes. You also see the direction of the wind in the sand dunes and also appear in the vegetation. So one reason why we have Pinus persistence is likely the edaphic reason of sandy areas in this region. And also the climate of the eastern and western part of the country is different. There is much more Atlantic influence in the western side of the country. The summers are less warm and the precipitation is more. That would not in itself explain the persistence of Pinus, so we need to involve this edaphic control in it to understand it. You also see that Betula and Quercus are also important and present in the landscape, but they do not show a major spread in the early Holocene. Quercus and also Corylus increases approximately at the same time than in the Great Hungarian Plain, so in the eastern part. In this record it's 10.5 K, but it's less expressed, this expansion, because it's shadowed by the high Pinus pollen percentages. And another important difference in the history of the regional forest succession in the western part of the country is the much earlier arrival of beech in the western part of the country. It's dated in this diagram to 8,600 Kbp, when you see that beech form reaches up to 20–30%, together with Corylus, Ulmus and Quercus is also very important. And that's the time when Pinus decreases in the landscape. So this is a typical vegetation succession from the west, and also important, this dual peak in the Fagus pollen percentages, suggesting its expansion first at 8.6 and the second time somewhere around 5,400 years ago when Carpinus expanded on the Great Hungarian Plain. So there are similarities, but there are major differences in the vegetation history. This map shows the distribution of wooded steppe, or in other words forest steppe covered areas in the Carpathian Basin and adjoining areas. And if I'm right, here we see this extension towards the Czech Republic, but you see we have very large areas covered potentially by wooded steppe vegetation in the lowlands of Hungary, and of course little or nothing in Transdanubia. And the site I'm going to talk about is coming from the northern part of this area, and researchers have long studied, the botanists mainly and ecologists, the history of the steppe flora in Hungary, which according to this map has several influences from the west, from the east and the south, and migration pathways have also been developed for different steppe components. And this way is very likely the migration pathway of Palearctic continental steppe elements towards the northeast into the basin. And another pathway was also demonstrated, very important, a Pontic Pannonian warm steppe species likely arrived from the east along the Danube corridor. And also we have a considerable share of submediterranean steppic elements in our vegetation, which likely arrived from the south to the basin. But there is a big question marks when these species arrived into the Carpathian Basin, whether they survived the glacier fluctuations in the basin locally, or they were extirpated and migrated in the Holocene interglacial period again. And how to explain this? So one way to study this is using pollen and plant macrofossil analysis of the deposits I showed you before. But before we going into the details of this study, I would like to show you a migration theory. I don't know how many of you are familiar with this. This is a so-called cornerstone of Hungarian botany, this uphill-downhill migration of the steppic herbs that dates back to the last centuries already, with the first studies of the Hungarian flora by Kerner and Borbás, who noticed that 90% of our steppic flora elements also appear in the hills, in the North Hungarian hills and the Transdanubian hills. So they found a connection between the lowland steppic vegetation and the hill vegetation, and tried to explain it. Where were the survival points, where these herbs appeared first, how climate influenced the population movements, and came to the conclusion that likely the Hungarian hills harbor refugia populations of some of these steppic herbs during the glacial periods, and mainly in the south-facing warm microclimate slopes of the hills. And during the warming periods, these refugial habitats serve as starting points of migration towards the lowland areas, and also vice versa. When the lowland area becomes covered by forest, totally covered by forest, then these south-facing hills of the mountains provide refugial habitats for the steppic flora. So the uphill-downhill migration theory has a long tradition in Hungarian botany, and several genetic studies started to deal with this issue recently. But according to this theory, the Pontic species were not migrating to the basin from the south constantly with interglacial-glacial fluctuations, but survived in the basin. So for most of the steppe species, or several of the, except from the submediterranean and Mediterranean elements, this theory assumes local survival in the glacial periods. Bálint Zólyomy was a famous Hungarian botanist who studied, was the brain behind the map I showed you about the potential vegetation, and he also studied the remnants of the lost steppic areas, and particularly the lost flora. And he had a hypothesis about the Holocene vegetation history of Hungary. And according to his hypothesis, these pontic warm steppe species, so he refused the Matra, Paleo-Matra, so the uphill, downhill migration. And he suggested that these pontic warm steppe species expanded northwestwards into the basin during the so-called boreal and Atlantic phases, climatic phases. Of course, at the time there was already a debate on how much the lowland area has been forested in the boreal and Atlantic phases, and the pollen diagrams suggested a considerable forestation of the lowland before human impact, much more than depicted on the potential vegetation map. But there was a period, according to him, in the boreal, approximately between 10,000 and 8,000 years ago, when the climate of the lowland was drier and warmer than today, and the steppes, climatic steppes, expanded in that period. And according to him, this was the time period when most of the pontic species migrated into the Great Hungarian Plain from the direction of the pontic areas along the Black Sea area. So there was, as I just showed you, there was a lot of debate, a lot of hypotheses put forward about the development of the Hungarian plain, but none of them really answered by paleoecological techniques properly. So the research questions, my research questions when I studied this question were that if we can prove that at least part of the Great Hungarian Plain were continuously forest steppe covered throughout the Holocene, so they were not becoming totally forested. And I was interested in the canopy composition of the forest stands within the forest steppe landscape, and how much it has changed throughout the Holocene, and how the prehistoric and historic human population influenced the share of woodland in the Great Hungarian Plain. That's what I'm going to talk about in detail in a couple of minutes. If we can differentiate between the vegetation histories of the continental and submediterranean forest steppe types. I haven't mentioned that we have two types of forest steppe. One is the continental, the other one is the submediterranean type. The one differs in species composition. In the continental type, beside the Quercus species, Tilia takes also important role, and also elm species are important. Whereas in the submediterranean forest steppe, Quercus pubescens and Quercus cerris, Quercus robur are forming stands, and it's a more open character forest steppe area. And I was also interested in if we can see stepwise changes in human-induced vegetation alteration, and if it can be connected to mass population movements in the Great Hungarian Plain. So some details of the area of the study. Here you see the pollen diagrams that are available from the literature. The problem is that some of these pollen diagrams, and many of them, are not dated at several points. Only 1 or 2 radiocarbon dates are available, so it's very difficult to reconstruct a continuous vegetation history, or they are fragmentary. And the map shows also the location of this very detailed pollen diagram from the Sallóhát area. And the location of Sallóhát is also indicated in this geomorphologic map, which is about the Polgár area. This is a very famous area archaeologically as well, because very extensive occupation has been very well documented in this area, partly because of the motorway constructions in Hungary, which really boosted archaeological research at that time. and partly because of very famous tell and flat sites have been recovered from this area in the Neolithic period, mainly Middle and Late Neolithic sites, and also very detailed zooarchaeological and archaeobotanical studies have been made in this area. The map shows the location of the higher lying ground with the older paleo channels near the village Tiszadob and also near the city Polgár. These are the places where most of the Neolithic and later occupations have been documented. And you see the Holocene alluvial landscape of the Tisza river here with the Holocene and late glacial paleo channels. One of them is Sarlóhát, which provided a nearly 8 meter long continuous Holocene sediment from the area, and with the help of the AMS radiocarbon dating of very tiny organic fragments, very tiny seeds, it was possible to build a reliable chronology in this area. Just briefly about the geomorphological evolution of the area. Probably some of you already heard about the movement of our big river, the Tisza River, which flew in a completely different way in the last glacial period, much nearer to the edges, to the foothill zone of the eastern Carpathians. But tectonic movements in the basin around 25,000 years ago resulted in a very quick movement of the channel towards the north, when it's called the Záhony avulsion, after the name of the city Záhony in the very northeastern corner of Hungary, where this channel, Paleo-Tisza channel, has been abandoned and moved to the north and also to the west, and started to take its flow through the Záhony area and also Tokaj, Polgár, and coming down as it is today. The reason I mention it, because it has got a very, very strong influence on the groundwater level table of the Nyírség area and also the Hortobágy area. When the Tisza has moved to the north, then other channels, not shown here, but flowing down to it from the north, quickly moved upwards. So the tributaries already reached the Tisza River in the north. So this area lost its fluvial activity. So and that resulted in a considerable decrease in water level. And also that's one reason why salinization of the land of the Hortobágy has started. So there was a very big change around 20,000 years ago in the geomorphology of the area. You see the same on a 3D digital elevation model. Again, the location of Sarlóhát. The reason I show it is because in this map you can clearly see that Sarlóhát lies in the seasonally inundated area, and its modern vegetation, of course, it's today heavily canalized, and agricultural lands appear around all of these channels. So plowland is typical, and grazing is also typical. But even before the 1940s, when this canalization process started during the time of the 1840s, sorry, even during the time of the Austro-Hungarian Empire, this area beforehand received much more water and was seasonally inundated. That also means that its potential natural vegetation is mainly alluvial oak, ash, elm forest in the alluvium. But in the Löss plateaus, you see the Löss plateaus at a higher elevation. The natural vegetation is Löss steppe grassland and Löss steppe forest steppe. We used loss and ignition analysis, pollen analysis. We also studied the green algae and also did a very detailed major and trace element analysis on this record. And here you see the sediment stratigraphy, the loss and ignition profiles, and the age depth model that shows that sediment accumulation in the early part of the Holocene, this is somewhere 7,000 years here, and you see the time scale here starting at 11 and up to about 7,000 years. It was a very fast accumulation, meaning that the deposition time 1 centimeter is representing less than 10 years in this part of the record, but then it's slowed down and it's connected to the channel movements and the inundation of the channel. So this fast sedimentation means that it still received annual floods with a considerable silt and clay content. But when it became really detached from the main river channel, then the sedimentation rate decreased considerably. And if we look at the pollen percentage diagram from this side, and if we want to see how the open land and the closed forest area changed, one particular measure we look at is the arboreal pollen percentage. It's here shown by black, so it's a summary pollen diagram. For you, some of you who are not familiar, here we show the depth scale and the time scale. So starting from today, going back to here, in this case, 11,500 years ago. And these are pollen percentages. On this block, you see up to 100%, so this summarizes the changes in the pollen diagram. And in gray, you see the relative frequency of herbaceous pollen types. And their relative frequency usually can be connected to the area covered by naturally open habitats in the pollen source area of these paleochannels. Modeling of the pollen source area in this case has not yet been done, but using similar studies, we can say that the pollen source area of the paleochannel, I don't know if I show it here, the local pollen components usually come directly from the floodplain, but so that's the effective pollen source area, meaning that 45% of the pollen rain comes from this area, but the remaining 55% comes from a much larger area. That likely incorporates the entire floodplain zone and also the terrace areas. So, but what you see on this pollen diagram is that no matter where we are in time in the Holocene, this the share of the arboreal pollen is only in a few cases go up to above 70%. Remember this value 70% because in the later figures it will be important. So generally lower, and I will talk about this human impact, which is very visible from 3,000 years and even earlier. So just a general look at the pollen diagram already suggests that this area has not been covered by closed forest any time during the Holocene. But if we go more into details, and this slide is I put it here because some Czech scientist has made considerable progress in quantitative palynology, because there are nowadays much more sophisticated ways of inferring past forest cover in a landscape using modern examinations, and a model which is called the Reveals model, where you can translate your pollen percentage data to real vegetation cover. But it requires a very, very detailed modern vegetation pollen relationship survey. This has recently been done in the Czech Republic by Wojtek and his colleagues, so mainly the Prague team. And in the Czech Republic there is already application of this method on pollen diagrams that cover the Holocene period, but unfortunately we haven't yet done it yet. So the aim is to collaborate with the Czech scientists and first try to use these pollen productivity estimates for the Czech sites, and then also to build calculate pollen productivities in Hungary and translate this diagram into a real vegetation cover diagram, because at the moment this is just a pollen diagram where the representation of the species or pollen taxa is biased depending on the pollen productivities of the different taxa. But when we published this paper in 2010, then we could use other techniques like the biomization technique. This is when you use the pollen spectra to infer biomes. This is also based on comparing surface pollen spectra with modern with fossil pollen spectra. And using Planck functional types, you derive biomes. And here you see on the left side of the figure the steppe biomes and the affiliation of the pollen samples to these biomes. In the middle, the forest steppe biomes, so temperate deciduous wooded steppe or cool mixed wooded steppe. And on the right of the diagram, deciduous forest. And when we do this biomization, we use this 70% criteria on the basis of this map, which shows the potential vegetation of Eurasia with the different vegetation zones and the percentage arboreal pollen in the surface pollen samples. And very important is the blue area here, which shows the wooded steppe, subcontinental and submediterranean, oak and mixed broadleaf forest steppe zone, and the percentage of arboreal pollen. If you look at this figure, it will immediately be visible that this 70% criteria is just really not appearing in every pollen sample, particularly those that are closely connected with the closed forest regions, so appear relatively close to the closed forest areas, have higher arboreal pollen percentages, and those that are closer to the steppic areas are below 70% in some cases. So this 70% criteria is a very arbitrary. It could be changed, and it's very much influenced by the surrounding landscape. So it's very important to be aware of this. Therefore, these biomizations, so biome affiliations, will be also affected by small changes in the arboreal pollen percentages, meaning that in some cases you end up with a closed forest reconstruction, no matter if it's just 2% more arboreal pollen. But generally, if you look at this figure, very important is that most of the samples are reconstructed as wooded steppe throughout the Holocene. I forgot to mention that we studied two cores from this site. You see that the central location at this core is in the middle of the Paleochannel, slightly shows more closed forest indication, and that one which is closer to the shore of the lake it shows more open habitats. But both of the records shows a very abrupt shift towards the warm steppe biomes in the late Holocene, around 2,800 years ago. You also see the indication of steppe by the relative frequency changes of the steppe indicator taxa, also showing a similar picture, higher, slightly higher in the early Holocene, and then a big increase around 3,000 years. We also did a micro and macro charcoal analysis in the sediment, and I only show you here the charcoal accumulation rates of the micro charcoal. I don't know who is familiar with this technique, but this is a measure of past burning of the landscape. So how frequently fire occurred in the landscape. And there are several publications where we use this curve and several others from the region. And it seems now that for Eastern Hungary and also for the Eastern Carpathians, the early Holocene period, up to 7,000 years, is generally characterized by much frequent fires than the periods afterwards. And clearly in the last 3,000 years, you can see anthropogenic fires in this area. The anthropogenic fire history, it differs from site to site, but in Eastern Hungary and also in the Eastern Carpathian Mountains, it seems now that most of the sites or all of the sites show much higher micro and macro charcoal values in the early Holocene, and this is likely connectable to solar insolation, which was higher in the early Holocene. Higher incoming summer insolation resulted in increased continentality, but very importantly, these ecosystems in the early Holocene were fire tolerant and also vegetation succession was very likely influenced by the returning fires. So this was nicely shown in the Charlohat area by this record. And we also made a compilation of the aforementioned pollen records in the area, as I told you, with very different time resolution and very different age depth models. So we decided only to characterize the arboreal pollen percentages in these records in each millennia. So we calculated the minimum and maximum values within this period and the most frequent value, and the red line in each time window that shows the 70% criteria. If we look at this figure in detail, then we see, depending on the location, these locations numbered by or shown by A are coming from the North Hungarian hills, and the numbers increase with the decreasing latitude. So 21 is the southernmost site, and try to follow it, these are coming to the north. So generally we can see that in the northern part of the Hungarian plain we see higher arboreal pollen percentages in the early and mid-Holocene period, and as we move down to the southern part of the Hungarian plain, the forest cover, or the arboreal pollen percentage inferred forest cover, was less in the early Holocene and throughout the Holocene. That's one conclusion what we can make. And we can also look at the human impact start directly around 3,000 years. The reason this figure stops at 3,000 years is that because after 3,000 years all of the pollen diagrams have very little arboreal pollen. So in the Hungarian plain we can generally say that arboreal pollen, the human impact in the last 3,000 years was the major trigger of arboreal forest cover. So that became very, very strong, but it's also visible already in this time window 4,000 to 3,000 years ago. So the major conclusion of this research was that we can demonstrate that in the Great Hungarian Plain, temperate deciduous wooded steppe persisted through the Holocene. So I think it's very important to point out that there was not a time period in the Holocene when this area was totally forested. It's a much easier situation in the Great Hungarian Plain than in the Czech Republic, where you have a restricted distribution of the steppic areas surrounded by likely forested landscape with closed forest. You've seen examples that when you have large forested areas nearby, that will strongly influence the arboreal pollen percentage values. So pointing out open landscape becomes more difficult. But since in the Great Hungarian Plain this is a vast area with half wooded, half not wooded vegetation, it was a relatively easy task to point this out. And I mentioned the view that the boreal period was a climatic steppe in the Great Hungarian Plain according to earlier hypothesis by Zólyomy, and we came to the conclusion that contrary to this earlier view, open vegetation did not reach its greatest extent in the Great Hungarian Plain during the so-called boreal phase, but earlier between 11,400 and 10,200 years. So the earliest phase of the Holocene was the driest, which is called in the old Blitz-Zernander scheme the pre-boreal phase. And forest cover in fact increased in the boreal phase. We also concluded that, as I showed you, wildfire apparently played a role in maintaining vegetation openness prior to 7,800 Cal BP, although after this date fires were less frequent, but came human impact instead of fires that helped maintaining vegetation openness. And human impacts very seriously started at 3,000 years ago. I promised to talk about the archaeology of the area and the human impact more in details. I already mentioned you that this area is very important, very well investigated archaeologically. And one way to do archaeological survey in an area is to do archaeological field working. This is the Polgár area where both Hungarian and English archaeologists did field working. It means that they are going in a gridded surface area and they are just collecting stray finds of pottery mainly, and detect and examine the potteries and connect them to different archaeological cultures. And by doing this, they can build a so-called population history of the landscape, which is much more detailed than a broad-scale archaeological survey. And this happened in this area. And here you see the results of this for different time periods of the Neolithic. It has also been done for later periods. So back to the geomorphology. In this map, yellow is the higher ground and white is the alluvial area, and the red spots indicate horizontal settlements, and in this case these are stray discards, so meaning just only single potteries were found. And this is representing the Middle Neolithic phase, which is in this part of the country was dated to 7,400 Cal BP approximately. So even this Middle Neolithic first occupation in the area, which can be already traced in the archaeological records, is quite old, 7,500. And you see a major increase in the finds, the archaeological finds, both stray discard, pottery shreds, and also tell settlements in the Middle Neolithic, Alford linear pottery culture period. So this linear band ceramic culture also reached the Czech Republic. So I think it was the time of massive population movement, mainly in western Transdanubia and towards the north. But this area also became much more populated, and very importantly, some finds also appear in the islands within the alluvium and the alluvium itself. And as we move to the late Neolithic period, here you see some of the archaeological excavation of these LBK sites, even some skeletons were found. In the late Neolithic period, although the number of stray finds completely decreases, very important is that large flat sites and tells have been found in this Polgár area, in this lying Pleistocene terrace surface, on the basis of which a population reconstruction has also been made. This is the late Neolithic period with a few finds showing the meander here, showing the location of this tell and flat settlement. And you see the geomagnetic results, which shows that there was at least one tell site in this area surrounded by ditched channels, and also a very big horizontal flat site here with 434 houses, so it's not a small site. And the estimated population number was 2,100 to 2,600 people. So in the late Neolithic, it means that there was a massive population increase, even compared to the AVK, so the linear band ceramic cultural period, but it was much more concentrated on the upper lying areas. Here you see again the tell site. Today in the landscape it's not very fancy, but when you do a magnetic survey, then you see a beauty under the ground. And Pál Sümegi also made a tentative vegetation reconstruction of the area. This is when we come to the local geomorphology influenced differentiation of the different type of vegetation within the alluvium and also in the Pleistocene lag surface. And the hypothesized vegetation cover prior to the Neolithic, of course, was gallery and floodplain forest in the floodplain area, and forest steppe cover in these Pleistocene lag surfaces with some original steppe. So the assumed impact of these Neolithic people was the thinning out of the gallery forests, and of course the opening up of the forest steppe zone in the Loess Plateau areas. So if we assume what it means in terms of pollen composition, then you would have to find less representation of the gallery forest and alluvial forest elements that must have been oak, elm in this period, and also fraxinus. And also this wooded steppe area was likely oak dominated, so we have to find a decrease in oak probably. So that's what we were trying to do, to zoom into this part of the record and see what changes we see. And we also did with John Chapman, who is an archaeologist, studied this area, a local archaeological survey around the meander to see that locally, compared to this regional picture of human impact and human occupation, what we see along the meander. Of course, we expected much less stray finds because we didn't expect permanent settlement in the alluvium. But if people were visiting the site, visiting the alluvial area, they must have left behind some kind of pottery shreds, etc. And of course, we did find, and you see the meander shores, in the northern shore of the meander, several concentrated stray finds also in the southwestern corner, and a percentage representation of these potteries from the early Middle Neolithic to the modern times. What is interesting is that the largest number of finds date to the Middle Neolithic Avika, so the linear band ceramic culture period, and of course to the post-medieval time, but the late Neolithic, when these largest settlements were found in very concentrated places, there is no indication of local presence in the alluvium. So after this introduction, I try to answer or give some information on the basis of the pollen analysis, and also supplemented by the geoarchaeological survey on how the people exploited the landscape, what we see in the pollen diagram. And for that we focused into the period of the Neolithic, and you find more details of this in a publication by the team published in the Vegetation History and Archaeobotany. And the first cultural period is the Körös culture, without any finds in this area, without any pottery in this area. There is increasing archaeological research in the area which shows that the Körös culture did not stop in the middle of the Great Hungarian Plain, but Körös cultural group also reached the northern part of the plain where Sallóhát is situated. But in this area, the archaeological survey did not find so far any evidence for Körös cultural occupation. If you look at the pollen diagram, however, we still see some very remarkable changes. First of all, in this figure, the arboreal pollen cover is expressed in a different way, so the woodland cover is expressed in a different way. We used arboreal and non-arboreal pollen ratios instead of the pollen percentages. This provides very similar results. Maybe the peaks and the lows are more expressed if you express it as ratio instead of just percentages. So what we can see is that even though local human impact cannot be detected, there is certainly a decrease in the forest cover, further decrease in the Körös period, and also a decrease in the charcoal concentration, suggesting that if people were present, if people were cutting, if people were disturbing the local local forest, then it was done by cutting and not burning of the forest. Another an important change in the pollen diagram is the increase in the Canopodiaceae family. Canopodiaceae cannot be determined to species level using pollen analysis, unfortunately, but it's a very important human indicator. Usually it can indicate disturbed ground, generally trampling, and also appears in crop fields, but also a natural constituent of the floodplain vegetation. And I just show you some example, one example here, when Chenopodium grows on the seasonally dry Paleochannel edges. So it's difficult to interpret these diagrams in alluvial setting, because you have to separate the human impact from the local likely edaphic control changes that can also be connected to changes in the water level fluctuation in the Paleochannel. So in this publication, we carefully interpreted this Chenopodiaceae increase, because there was also an organic content increase in the sediment. We came to the conclusion that it can both indicate human impact, but it can just as well indicate a drier Paleochannel edges during the summer with increasing water table fluctuation. So at the moment, the Chenopodiaceae cannot be decided whether it's human impact or not. Of course, it will contribute to the arboreal pollen decrease, but you see another important change is the increase of quercus. And remember this, because I will show it in other diagrams as well, this quercus increase, which is appearing around, starting at 8,200. The increase of quercus precedes the Kurösh cultural phase, so it is very likely that it's not necessarily human related, or the dating of the diagram is imprecise. You see that the radiocarbon dates come from these points. So there can be some accumulation rate change within this period, and the radiocarbon dates can also be biased, but we don't know at the moment. And if you look at the serial pollen curve, serials are, in this case, all Poaceae pollen grains that are bigger than 40 microns. These can include wild species as well. But very interesting is that the first increase of the serial pollen curve is also appears before the Kurösh cultural phase, already at 8,600 years ago, which is not a unique phenomenon of this diagram, which is quite common in European pollen diagrams, also from the Alps, that the archaeologists demonstrate plough land and arable fields couple of hundred years later, then that become detectable in pollen diagrams. It's an unresolved problem at the moment, whether they really indicate arable farming in the area earlier than by archaeological remains, or these are wild cereals, representing wild cereals. But these are interesting, still open questions. If we move to the next period, this is the already the early linear pottery culture, which is locally called the Satmar culture. It's a very short time period, very difficult to locate it exactly in the pollen diagram, because it's just 200 years altogether. But the pollen diagram in this period clearly indicate some changes. First of all, there is a big charcoal peak, which can be human related, and there is also further decrease in the arboreal pollen cover. And we also find a change in the Fraxinus pollen representation, still very low quercus, low and increasing, so up and down quercus, and the Corylus seems to be also influenced. And this is a time period when we have the highest Chenopodiaceae pollen representation in the record. So this is the Avica period, where there are many sites in this period, and also in the alluvium itself. And and it's the second part of this phase, this Alfred linear pottery cultural phase. So it cannot be totally separated from the one before that. When the Fraxinus increase likely indicates secondary succession after forest cutting, and also very important, the increase of Artemisia in this record. We have compiled a table of what herbaceous taxa would indicate what sort of natural environment and where they appear in human influenced environment. And Artemisia is typically connected to pastoral farming, so the grazing indicator. So we inferred from this that the increase of Artemisia in this period is likely an indication of grazing in the alluvium itself. Here you see examples of grazed meadows with increased Artemisia representation, and it will be more important, even more important in the later phases. And finally, the tissacultural phase with this large settlement, but hardly any findings in the alluvium. In the pollen diagram itself shows the best expression of pastoral farming in the area, and the first appearance of this is the Latin names are replaced by the Hungarian names here. But if you go back, you see the Latin names here. This is Secale cereale, which is usually appeared in the Neolithic as a weed in the triticum fields, in the what is it in English? The wheat fields. And when they find it in the pollen diagrams in the Neolithic period, they usually connect it to the to arable farming, because Secale produces much more pollen than triticum. So it usually indicates you the presence of cereal fields in the area. So you can see that it appears here. But we also have to mention that we have cereals naturally or in the earlier layers as well. So cereal Secale species, wild Secale species also appear in the alluvial landscape, making the detection of human impact even more complicated. But if we go back to the Artemisia peak, we can see that it's the most intensive in this late Neolithic phase, when the population is the largest in the area. I mentioned that there were a lot of very detailed archaeozoological and archaeobotanical studies made on the excavation material. And the outcome of this research are summarized on this slide for the Neolithic periods in general, but most of these results relates to the late Neolithic period, where the flat settlement and the tell sites were found. So they mainly represent these points, the land exploitation techniques of the late Neolithic people. As you can see that there was a lot of evidence for hunting, so the people who lived here used the alluvial plain for hunting very intensively, and the fauna of the alluvial plain was very, very rich in species. And they also found that at the rondel, which is the tell site, they found higher meat consumption, and archaeologists connect with tell to a ritual life. It was probably a church at the time, they say, so that's why they connect this higher meat consumption to the ritual life. And the wild fauna was very interesting. The presence of equus was really in a good connection with what we found in the pollen, indicating the presence of natural open habitats in the landscape. They also investigated the cereals, the main cereals. You see what cereals were found, a very rich composition again. And people were consuming also green pea, lentil, Vicia faba. So they had a skill in arable farming. And there was also a lot of gathered fruits, cornelian cherry, particularly Prunus spinosa, Sambucus ebolus. And on the basis of the wheat flora, there was also a reconstruction of the plowland locations. And that was very important because some of the weed species indicate wet habitats in these cereal assemblages. And by the late Neolithic, the conclusion was that the plowland some of the plowlands were located in the terraces near the settlement, but the people started to exploit also the seasonally wet areas at the edge of the alluvial plain. And they explained it with a dual technology that high yield, high risk is the seasonally wet area, because if the water level increases very suddenly, then they will lose all of the cereals they are going to produce. But if they are lucky, they get high yield in those places. Whereas in the flat surfaces, there was a shortage of arable land available already at that time. And it's a constant, more reliable but lower yield environment. So it was nice to see that the archaeobotanical investigation could already point out the difference in the movement or placement of the fields. And they also found stipa seeds in the archaeobotanical assemblages, which again indicates that there were naturally open environments. And there was also a very detailed charcoal analysis done in this, in the charcoal found in the archaeological sites, and that's summarized in these plots, in these circle diagrams here. The work was done by a Polish scientist, Magdalena Moskal-Hoyó. She counted thousands of charcoal from these archaeological excavations, and she grouped in a publication into archaeological periods. This is the period of the Middle Neolithic, and this is the two bar diagrams of the Late Neolithic. I know that it's a bit difficult to read this figure, and next to it I put the pollen composition of the same intervals in the pollen diagram, just to compare how they compare, but I try to help to interpret it. Very importantly, I think the charcoal studies added an awful lot to the pollen analytical investigation by pointing out in the middle and also in the Late Neolithic, particularly in the second assemblage in a Polgár 6 site, that beside the dominance of oak, black is the oak here, so certainly the assemblages are dominated by oak. Cornus was very important, which is a shrub, and unfortunately it cannot be identified to species level on the basis of charcoal. And if you look at the pollen doesn't appear frequently in the pollen diagrams because of the poor pollen production of Cornus. It can be both Cornus sanguinea or Cornus mas. It would be important to further identify the species, but I showed you that Cornelian cherry, so Cornus mas, was present in the archaeobotanical findings. So it's very likely that at least part of this Cornus is Cornus mas. And if Cornus mas is present, and it likely grew on the Löss plateaus at that time, where the settlements were, then it also has some inferences for the composition of the wooded steppe vegetation, which nowadays you often see such mixture of Quercus pubescens, other Quercus species, and Cornus mas in Bulgaria and Turkey, in a much warmer sub-Mediterranean type of wooded steppe. So this data at the moment suggests that in this Neolithic time period, for which we know that the summer temperature was warmer than today because of the higher insolation, this part of the lowland was likely characterized by this Mediterranean, sub-Mediterranean type of wooded steppe, where Quercus pubescens was present together with Cornus mas. I'm not saying that it's evident that this was the dominant, but these data suggest that it is very likely. And it's also important to point out that without the help of the charcoal analysis, we would not come to this conclusion, because the pollen composition just simply lacks this important species that's important to characterize better the forest structure at that time. Another difference is the Corylus. You see the Corylus here is very prominent, I showed you. And if you look at the charcoal assemblages, Corylus is not important. It's present, but it's not the most important species. This, first of all, suggests that Corylus was likely overrepresented. It's an ample pollen producer. And on the other hand, it can also suggest that Corylus was not common in the plateau environment where it was this sub-Mediterranean type oak wooded steppe, but it was more connected to the alluvial landscape, which is very controversial because when we reconstruct Holocene environment, Corylus is usually taken as warm indicator, indicating warmer conditions than oak itself. And it's a bushy type vegetation what we reconstruct. But if you look at the present distribution of Corylus avellana, where it forms pure stands, it's very few places in Europe, and they are usually located in Germany and Ireland. And these are wet places. In Scotland, Corylus usually accompanies riverbeds, and some of these places are influenced by seasonal water level movement. So I think at the moment, and this is an issue which is discussed in vegetation, historical vegetation or vegetation succession, that we are not aware of the niche what Corylus has been situated in during this early Middle Neolithic period, and this subject should be investigated more in detail. But this figure is also contributing to this, and the pollen suggests that either the location of the Corylus stands was different, further away from the human settlements, or it's strongly overrepresented in the record. But we also know from many, many archaeological sites that people used hazel, not just hazel fruits, but they coppiced hazel, and coppiced hazel rods are very commonly used as fences in this period, and particularly in the Alps and northwestern Europe, many direct findings indicate the use of Corylus in this period. So that's what I wanted to point out with the comparison of these two analyses. And as I mentioned, these are some tentative interpretation of how these steppic woodlands look like in this early Middle Holocene Neolithic period in this landscape. So as I mentioned, I find the best analogues in Thrace, in Bulgaria, and northern Turkey today. And since this project is about coppicing, and I also studied coppicing in scope of this project, but very small results, I would like to show what we found in the Great Hungarian Plain in some of these sediments. This site, Nagymohos, is a peat bog in the hills of Hungary, in the Putnok. It's called the Putnok Hills. In fact, it's not very far from the Aktelek area. The peat bog is one of the very few sphagnum bogs in Hungary that has accumulated peat, sphagnum peat, in the Holocene. The elevation of the site is nearly 400 meter, but relatively low. And this is the Holocene pollen diagram from Nagymohos, showing the settlement number from a larger scale archaeological survey in 50-kilometer radius of the peat bog. And this is the number of settlements they found in the area. And you can clearly see that in the Alford linear band ceramic cultural phase, there was an increase in population in this area, and also in the book cultural phase. This is the late Neolithic period, the Tisza-Herpálycsőszalom from cultures we were just talked about, and the settlement number is very low in a regional survey. But if you look at the Artemisia in this environment, that's shocking. So this is a closed forest landscape, over 80–90% arboreal pollen, but you can clearly see the impact of these late Neolithic people, suggesting that in the Nörby river valley, this is the Sajó river is flowing not very far from this peat bog. Likely people were using the landscape for pasturing, so for grazing. And I don't know if it's because of the low number of archaeological survey in the area, or because of the closed forest nature of the area. It's much more difficult to do archaeological survey here, but certainly the archaeological result and the pollen result is in mismatch with each other. But if we go back to the linear band ceramic phase, it's interesting to see that Quercus increases in this period, and you have also seen this increase in Quercus and decrease in Corylus in the Charlotte diagram, but it started much earlier. So that started here, in fact, 8,200-ish in that diagram. But here it's only 7,400, and it's relatively well dated. There is a radiocarbon date just below that, so it's very likely that we can clearly connect it to the AVK cultural phase. And you also see that there is a Fraxinus increase when the Corylus decreases, so some signs of secondary succession there. And if we look at another diagram, Holocene pollen diagram, not very far from here, also in a more forested area. This is called the Berek Plain, which receives much higher precipitation than this part of the Alford. Today both beech and carpinus is present in its vegetation. And if you look at the arboreal pollen, it's much, much higher than further south. Here you can also see an increase in Quercus and decrease in Corylus, and ups and downs in the diagram. And Fraxinus is more expressed in this period. And this diagram also shows a settlement number, and you see that AVK settlement number increases in this period, similarly to the previous site. So on the basis of these two diagrams, and also there are further studies in Hungary, in the Sirok area, which is also in the Middle Mountains, where much higher resolution pollen analysis was done. We suggest that this likely reflects the land exploitation at that time and not climate change. This appears for a couple of hundred years only, and also present in the accumulation rate diagrams. I'm not going into details of this, but you can express pollen as pollen accumulation rates. And pollen accumulation rates better represent population size changes and flowering changes of plants. But it's a very tricky measure because you need to estimate the sediment accumulation rate very, very precisely, and you need to have a constant sediment accumulation rate. If there are small changes and very abrupt changes in sediment accumulation, then you end up with false peaks and false decreases in accumulation rates. And unfortunately, in the Great Hungarian Plain, we do not have such a good deposits. But going back to these two slides, it seems likely that the reason of the Corylus decrease and the Quercus better representation is the coppicing of hazel. If you do it regularly, then you will get less flowering of hazel and better representation of other elements in the landscape. It doesn't mean that the population size of these taxa increases, and that's what we should see in the accumulation rates as well. So constant Quercus populations, you do not see it here, and decreasing Corylus accumulations. So that's what you need to use to detect coppicing, but of course you need to have much higher resolution diagram than this. And you should also, if the coppice cycle was longer than the reflowering start of Corylus, so when they cut the Corylus and it starts sprouting, and in the first couple of years there are no flowers on the shrub, but after I think 6-7 years it starts flowering again. And if the coppice cycle is shorter than 7 years, in this case, that means that you will not see it flowering. If the coppice cycle is longer, then you should see it flowering in between. And in a very high resolution pollen diagram, you should see Corylus pollen peaks and Corylus pollen decreases in these records. So this has to be studied more in detail. I think we have chance to do that in case of the peat bog, but I really doubt that in a paleo channel you can do it better than this. But comparing it with evidences from the same Neolithic period from Western Europe, it seems that these cultures exploited the woodland very much by coppicing them, and the coppice was not used for firewood but rather for building construction in this period. So finally, about the Iron Age, I mentioned you that the Iron Age shows a massive increase in land exploitation in the Hungarian lowland. On the other hand, if you look at the population size and the archaeological remains in this period, that's in the early Iron Age decreases. This is partly attributable to the nomad lifestyle of these people, and there has been a debate between archaeologists. There are two groups of archaeologists, one of them who are supporting migration, so migration from the east in this period, and new technologies appeared together with lots of people who came. And according to another group of archaeologists, very few people came. They brought in the technology, and the locals adapted the technology. Therefore, they investigate this question partly using paleoecological techniques. And John Chapman's, in this paper, what we wrote together, used the Charles-Louhat pollen diagram to examine this question. And he is the member of the archaeology group who is opposing migration. In fact, so he wanted to show out land use continuity in this time period, and concluded that it's the local population survives in this period. So one of the important culture groups who comes into the Carpathian Basin is the Scythians. And the Scythians bring the horse, a lot of new technical improvement at that time, but very few sites have been found, particularly in the early phase in the Great Hungarian Plain, and also in this area what we have studied. So focusing on that part of the diagram, you see this cultural phase starting 2,800 years ago. That's the onset of the Iron Age. What you see is that in the diagram, the first very remarkable decrease of the woodland cover was detected around 3,100 years. This is still the late Bronze Age period. And at the same time, this umbelliferae type pollen, which includes bidens in itself and Oenanthe aquatica. If you are familiar with the species, these two species appear usually on wet habitats in Paleochannel shores. They require some kind of disturbance, some of them. One of them is a nitrophilus species, but they are natural constituents of the wetlands. There's a prominent increase in this umbelliferae pollen on the meander shore, and in the meantime you see a decrease in Poaceae and a very sharp increase in Artemisia. So if you put these together, Artemisia is a strong grazing indicator. Poaceae is a bit strange, very difficult to interpret at the moment, why we have a very, very abrupt and steep decline in Poaceae, because Poaceae should come from the alluvial plain in itself, so it's a large pollen producer, involves several genera, but it seems that the impact of these people was that they created vast pastures in the alluvium, probably overgrazed the pastures, so large hordes of animals must have appeared in the alluvium, and that affected somehow also the Poaceae in this diagram. So we see a very strong human impact appearing. Again, we see a slight mismatch in the timing. It's the timing of the Prescythian period, slightly earlier than the first radiocarbon dates of the Scythians. But to me, it suggests a massive movement of animal, at least animal herds into the area. So our conclusion was that we found a continuity in land use between the late Bronze Age and the early Iron Age communities based on an agricultural and pastoral practices, but of course a much more expressed pastoralist exploitation of the landscape, which in itself suggests that something really big must have happened in that period, which affected this area at that time. And I came across with this paper. I don't know if any of you have seen it. It was published 2 weeks ago in Nature Communications. And this paper deals with a genetic study of human skeletons from the Great Hungarian Plain. It's a very exciting study because this is the first one that compares the human genome of ancient tribes in the Hungarian Plain to partly modern human genetic studies and also hunter-gatherer genomes that have been studied using fossil bones. With the improvement of the genetic methodologies, they are now able to sequence very important parts of the human genome that show some kind of SNPs. These are single nucleotide changes that appear in some kind of human populations and in other populations not. And on this map, on this figure, you see a PCA of the different cultural groups. Partly the hunter-gatherers are fossil, Western European Sardinians are modern populations, and the Caucasus people and the Asian Near East people, the representative genetic material, and also the early Neolithic Körös cultural bone from Hungary, which certainly shows affiliation or connection with the hunter-gatherer bones. So then, in itself, it suggests that, as assumed by the archaeologists before, these Körös cultural people were also meeting local hunter-gatherers, and they were mixing together, and some of the technologies were taken over by the hunter-gatherers. This this Körös bone comes from the very northern part of the Hungarian Plain, so from the very northern distribution limit of the Körös culture. If you look at the other Körös cultural skeletons and also the Avika, I think some of these are Avika bones are also present. They show affinity with Southern European people, especially Sardinia is an island where very ancient genomes survived in the local population. So the Sardinians are usually used as the most similar people to Neolithic people. So it indicates that there was migration indeed into the basin. So not only technologies but people arrived into the basin in the Körös phase. This analysis also shows they analyzed Copper Age and Bronze Age bones, that in the Copper Age the same population survives. So there is, at least with the study of these bones, there is no further migration into the basin. But during the Bronze Age, Baden period, there is two skeletons studied that show closer affinity with the Western European people. So this suggests migration from the north at 4,000 some hundred years ago. And in the early Iron Age, which is the period of the Scythians, the pre-Scythians, I showed this strong human impact. Immigration from the east can clearly be shown by the study of the few skeletons, I think it's only one skeleton, that show closer affinity to the Caucasus and the Near East. So the researchers interpreted this, it's the publication of Gamba et al., that there were three migration, they could point out at least three very strong migrations in the area. One in the Körös cultural phase from the south, 7,000, nearly 8,000 years ago. These radiocarbon dates are the dates of the bones that were used. So it doesn't mean that they could not come earlier, but that particular bone was dated to this period. And then the second in the Mako cultural phase in the Bronze Age, and the northern impact can be pointed out. And this Prescythian bone was dated to 2800, and it shows Eastern origin. So the question arises that then it seems to support the migration theory of archaeologists. So not only technologists, but people also came to the area. And if we consider that then there were large population movements, large technological revolutions at those times, they should also show up in the land use strategy. Whether they can be examined by pollen analysis, so if they show up in the pollen records or not, it's a good question. But if there was a major change, then they should show up. So I did a PCA using these ecological groups of the pollen taxa, what you see there, cereals, other crops, so simply just adding up the pollen percentages of them, fallow herbs, and see what the first and the second axis shows. If we can find changes in land use, what these categories may indicate. And what I found is really what we see in the pollen diagram, that the biggest change is 3,000 years ago when the Prescythian comes. In the Kurdish cultural phase starting at 8,000 years, there's minor change. In the AVK phase, we see some change in the first PCA axis, and I show you in a minute the biplot, how to interpret it. But clearly the major change at 3,000 years, so this broadly corresponds with the Scythian migration, and hardly any change in the Baden cultural period when the northern influence was detected by them. If we look at the biplot, so what is representing what, I think it's interesting to see these pale gray circles indicate those pollen samples that are coming from the early Holocene, when human impact, at least Neolithic human impact, was not yet detected in the pollen diagram. Some of these ecological groups, of course, appear in that period as well, and they clearly show dry steppe, affiliation with dry steppe, and also another important factor is the wet meadow herbs. So the first axis separates the samples along this dry, wet pastural indicators. So dry steppe, natural dry steppe, and wet meadow herb indicators, and also the typical steppe indicator herbs just group around these early Holocene samples. If you look at the cultural periods, the Copper Age and Neolithic, the Copper Age is this pink, the Neolithic is yellow, is very similar to each other, and so does the Bronze Age. And all the samples are just grouped around the steppe indicator herbs and just the very tiny movements towards the dry pasture indicators. So this first big change appears really in the Iron Age, and that's mainly towards the wet and outside this wet meadow herb spectrum, and also in the Middle Ages. So this movement here in the PCA1 curve is reflecting a movement towards wet pastures. So this is quite convenient if you consider that we are in an alluvial setting, and in the alluvial setting, if they start grazing, then the wet pastures will increase in the largest proportion in the landscape. So I would like to finish here, and I think I hope that I managed to give you some indication of the landscape changes related to human impacts in the Hungarian lowland. Thank you for your attention.